So good evening everyone and welcome to the fourth session of the course Introductory course in Real Analysis. Okay, so we'll begin today's session with some problems related to sequences and its convergence. Okay, so to begin with, let us look at this problem. So the question says that suppose you have a sequence xn which converges to 0. Okay, then can you talk about another sequence which is yn given by xn raised to the power n? Okay, so this whole question deals with this problem. Suppose you have some information. So convergence of xn is known. Okay, so can we say, can we conclude about the convergence of xn raised to the power n? Okay, so this is a new sequence yn which is given by xn raised to the power n. Okay, so this is the question. Okay, the overall. So the first question says it's a special as the limit. So you know the convergence of xn, that okay, xn converges to x, and in fact you know that the x is equal to 0. Okay, so the sequence is converging to 0. So can we prove that the new sequence xn raised to the power n will that also converge to 0? Okay, this is the first part. The second part says that the sequence converges to x, but now it's non-zero. Okay, so x can be any real number, non-zero real number. Then again the same question, will the sequence xn raised to the power n, will it be convergent? Okay, so more or less the question is same, but the only difference is the limit point. Okay, I hope the question is clear. So now to begin with, do you have any guesses? What do you think about it? What do you think? Is the first one true or false? Okay, so the answer is basically that the first one is actually true. Okay, and you can prove it very easily just using the epsilon definition. The second one is actually not true, and I'll give an example for that, where you will find that the sequence is converging to some limit which is not 0, obviously, because if it is converging to 0 then the result is true, but if it is not 0 the limit, then the result is not true, that the xn raised to the power n may not converge, it may diverge. Okay, so to begin with, let's go with the first problem. So given xn converges to 0, okay, and you have to show xn raised to the power n also converges to 0. Okay, okay, so to prove that xn raised to the power n converges to 0, we need to choose some epsilon, right? So just the standard way, so let epsilon greater than 0 be any arbitrary real number. Okay, then so what you have to show is basically, so let me write it in words. So you have to show that xn raised to the power n minus 0, which is again that, is less than epsilon for all n greater than equal to n naught. So you have to find some n naught for which this holds. Okay, that after n naught all the sequence terms are very small. Okay, so now we also know that xn converges to 0. So then as xn converges to 0, so xn, I can say xn minus 0. So okay, let me write in words. So for epsilon, okay, another epsilon I am defining, epsilon tilde equals epsilon raised to the power 1 by n, let's say this is greater than 0, there exists some n naught belonging to natural number such that this difference xn minus 0, this is less than epsilon tilde, okay, which is epsilon 1 by n for all n greater than equal to n naught. So just by definition. Okay, so this is just definition of convergence. Now from here what we can say is this mod xn is less than epsilon 1 by n. So for all in this, for all in greater than equal to n naught. Okay. Now if I take power, okay, then I'll get xn raised to power n, which is the same thing, taking mod and then taking power, or other way around. This is less than epsilon 1 by n, okay, for all n greater than equal to n naught. And this is nothing but this proves that xn raised to power n converges to 0. Okay, so this is just by definition we can obtain this result. Okay, now coming to the second one, I have one counter example for that. Okay, so I'll give a counter example xn. So my counter example will be like, so I'll have to find xn, okay, what will be it, so that xn converges to some x. Obviously it has to be non-zero. Okay, otherwise if it is going to 0, then obviously the limit we have proved in a part that xn raised to power n will also converge, and it will, the limit will be 0. So such that xn raised to power n diverges. Okay, so this is what we have to find. So we have to find the explicit sequence xn. Okay, so like maybe we can try going backward. Okay, so see, you want xn to be divergent, and what is the simplest example that you know which diverges? Can you give me some example of a sequence which is divergent? Any sequence? What is the simplest, I mean, example what you see? So let me, so you know, if I define a sequence yn equal to n, you know that this diverges to infinity, correct? And if you take, so basically you want this to be divergent, so I want this to be xn raised to the power n, okay, which diverges to infinity. So what will be my xn? Xn would be n raised to the power 1 by n, right? So now I have to show that this is convergent, and in fact you must be knowing that this is convergent, that it converges to 1. Okay, I'll prove that. So okay, so this is the hint. Okay, so this is the example what we can write. So define xn to be n raised to the power 1 by n. Okay, then my first claim would be, I'll prove this, that xn converges to 1. Okay, and then we'll show, then it's obvious that if I take nth power, okay, that is not going to converge at all, right? We know that n is divergent. Okay, so to prove this kind of thing, what you can use is basically, mm, maybe, so the, like, whenever you have some power, okay, nth power something, you can use the log transformation to make it simpler. Okay, so I'll use this transformation. So define yn to be this log of xn. Okay, so this is my new sequence. In other words, this xn is e raised to the power yn. Okay, that's the same. So when I take log, what I get is log of n raised to the power 1 by n, right? So what I get is 1 by n and then log of n. Okay, my claim is that this will converge to 0. Okay, so I'll have to find, so basically I'll have to find some bound so that which goes to 0, and then we can use sandwich theorem, or just by definition you can prove that this is converging to 0. Okay, so you note one thing. So you have this thing, right? So e raised to the power root x, okay, or any x you take, okay, root x, x raised to the power 1 by 4, whatever, you know that exponential is, has this kind of obvious bound, because this is a series, 1 plus root x plus x by 2 factorial plus root x raised to the power 3 by 3 factorial. It is a series. So this is greater than 0 for all x greater than positive x, right? And this is nothing but, this tells you that if I take log both the sides, what I get is root x is greater than equal to log of root x, right? And this is nothing but 1 by 2 log of x. So this gives you that log of x is less than equal to 2 times root x, right? So in this way you can write here that this is 2 raised to the power, sorry, 2 into square root n, and then you have in the denominator n, and this is nothing but 2 by root n, right? And now you know that this thing converges to 0, and over here also you can write so this n raised to the power, this also I can write it as, this is always going to be greater than 1, okay? So this log is always defined, that also you have to make sure. So this is always greater than equal to 0, okay? So this 0 less than equal to yn, and this, so by Sandwich theorem you can say, or even if you don't want to get into this, you can just take mod, okay? So okay, if you don't want, so there are many ways, you can just take mod, and then you can use Archimedean property to say that this 2 by root n can be made very small, right? That is the obvious thing we know. Anyway, so this concludes, this gives yn goes to 0 as n goes to infinity. So this is by Archimedean property or by Sandwich theorem, okay? So you have these two theorems from where you can obtain this. Okay, so now this proves that this yn goes to 0, and this would mean that xn, which is exponential of yn, this converts to 1, right? Okay, so we have got that my limit, this sequence xn is converging to 1, and another thing is that xn raised to the power n, but xn raised to the power n is equal to n, and this diverges to infinity. Okay, so we have got an example where the sequence is converging but its nth power is diverging, right? Okay, so this was about this first problem. Now heading back to the second problem, we have this is a kind of very good useful result which people often use. So what you have here is that suppose you have a sequence xn, okay, and what information you have, that whatever sequence you take of this xn, okay, that subsequence may not be convergent, okay, let's say, but it is having a convergent subsequence, okay? So the thing is that suppose xn is something that you have, what it says that if you take any subsequence, okay, xnk, so xnk is a subsequence of xn. Now this subsequence has a property, okay? So first of all, that this sequence has a property that whatever, so this is arbitrary sequence, okay? This is arbitrary, not specifying that one, any sequence, or maybe any I can write that any sequence subsequence I am taking. Now this subsequence will have a subsequence. Now this is kind of maybe unique kind of thing, that there exists a subsequence which is convergent, okay? So this every subsequence of sequence xn has one convergent subsequence, okay, and all the convergent subsequences are converging to the same limit point. So this is very important, that this limit is common, okay? So suppose xn is a sequence, okay, I gave you one subsequence xnk, okay, then this will give you a convergent subsequence. So let's say xnkl, okay, this is converging to x. This is what the theorem says. Now if I give you another subsequence, let's say xnk2, okay, how should I denote, or xnk tilde, okay, then this will have another subsequence xnk tilde l, which is also converging to x. So the limit points are always going to be the same. Okay. Okay. So this is the property that every subsequence has a convergence subsequence, and the limits of those convergence subsequences are common. Okay, so now let's, so okay, so when you have this property, so this is the property. Okay, let me keep it there. So when you have such property, then you can show that the sequence itself is converging. Okay, so suppose xn has this property, then you can show that the sequence xn is converging to x. A priori we don't have any uh, result about xn. Okay, so we just have one assumption that every subsequence has a convergent subsequence, all converging to the same limit. Then the original sequence is also converging to that limit, common limit x. Okay, so that's the property of this, that's the outcome of such property of the sequence. Okay. Okay, so how to prove it? Okay, so the proof will be via contradiction. Okay, so what we'll do, we'll assume that, okay, suppose xn is not convergent. Okay, then using the definition, we'll try to construct a sequence, okay, or subsequence which is convergent, and this will contradict, okay, in some sense. Okay, so let's begin the proof of this result. Okay, so the proof is by a contradiction. So, okay. Okay, so suppose, if possible, suppose xn does not converge to x. Okay, so what does that mean? Okay, so we'll have to negate it, right? So let me first write the definition of convergent, then I'll try to negate it. So when I say xn converges to x, what does that mean? This means that for any epsilon greater than 0, there exists n naught belonging to n, or maybe let me write k here because I'll be using x and k notation. So there exists k such that mod xn minus x is less than epsilon for all so what should I write? So for all n greater than equal to k. Fine. Okay, so over here, what will be the negation? Now we are saying that x and k does not converge to x, right? So x and k is not converging to x. That means that this property is not going to hold. And what does that mean? That, so whenever you have for every, you change it to there exist. Okay, so here you have for any, so now I'll change it to there exist. So that would mean just we have to negate it. So xn does not, so there exist epsilon naught greater than 0 such that, okay, now here you have there exists, so it will be now for all. Okay, so just opposite, if you have for all, you will get for there exist, and if there is there exist, you will have to write it for all. So there exists epsilon naught greater than 0 such that for all k belonging to n, now here you have for all n. Okay, so let me write it in this way, linear fashion, such that for all n greater than equal to k, we have this. Okay, so for all n greater than k, we have this xn minus x less than equal to epsilon. Okay, so for all k belonging to n, there exist n, okay, depending on this k, so I'll just write nk greater than equal to k such that this property does not hold, such that this xn this xn k minus x is greater than equal to epsilon naught. Okay, so this is negation of this definition. Okay, okay, so this is, let's say this, I'll name it as star. So we have this property over here, right? Now what we have to do from here, I'll try to construct a subsequence because I have to use this line, that every subsequence is a convergent subsequence, and this will give a contradiction. Okay, so see here we are getting, so let me write in this way. So suppose for k equal to 1, so this is saying that for all k there will exist nk. So suppose k is equal to 1, so for k equal to 1 we get n1, right? Now I'll so we'll get n1, for k equal to 2 we'll get n2, right, and so on. But the point is that may not form a subsequence, so we'll have to choose in a particular fashion so that we can say that this is a subsequence. Okay, so what we do, for k equal to 1 you define n1. So you know that there exists some n1. So n1 how will define, that n belonging to n, okay, or n is greater than equal to 1 such that mod of xn 1 minus x is greater than equal to epsilon naught. Now you know that because of a star, you know that this is non-empty due to star. Right, a star tells you that okay you will have some n1 such that, I mean this line I'm saying. So you know a star tells you that there will exist n1 such that this happens. Okay, now I'm defining n1 to be minimum of such. Okay, so why I'm writing n1 here. Okay, so now I'll define n1 to be minimum of all such quantities. So see, when k is equal to 1 you get xn1. Now you can get many, xn1 can have many choices, so I'll take the minimum of all those. Since it is non-empty and we know it is a bounded below set because we are taking numbers from natural number, right? So we know that n is greater than equal to 1. So in this case if we define minimum, this will make sense and this will exist. So I'll define n1 to be minimum of this. Okay, so in similarly for k equal to 2 you define n2 to be minimum of natural numbers which is greater than equal to 2, okay, such that this xn minus x is greater than equal to epsilon naught. Okay, and in the same way you can proceed, but now here the point is that you want it, see the subsequence has to be increasing indices. So n1 should be less than n2, n2 should be less than n3, like that. Okay, so here we have to make sure that we'll choose n1 n2 n3 in such a way that in an increasing fashion. Okay, that is always possible, that is something which you can always do because of the fact that suppose that n2 is equal to n1, suppose, then we'll drop this n2, we'll go choose n3. Okay, are you getting? So in case, so what I'm saying, the possibility is, suppose for epsilon naught you are getting n1 is let's say 5, okay, and n2 you are getting also 5. Okay, then in this case I will drop this n2, I'll go for n3. Then I know n3 will be let's say n3 is also 5, n4 is also 5, n5 is also 5. Okay, but n6 is not going to be 5 because n6 is greater than equal to 6. So n6 is always going to be greater than equal to 6, so nc is not 5, and n6 is greater than n1. So in this case this will be my n1 and this will be my n2. Okay, so what I'm trying to say, that you can choose this n1, you can choose these things in an increasing fashion, that you can always do. Okay, so based on this fact what we can say is, so without loss of generality it, mm, uh, we can assume we can choose the sequence nk, okay, k is equal to 1 to infinity in an increasing fashion, strictly increasing. Okay, in strictly increasing session. Okay, so what this means that n1 greater than this than n2 and so on. Okay, so what now I can write is, so x and k belonging to n is a subsequence of xn, right, such that x n k minus x is greater than equal to epsilon naught, right? This is how we are choosing this subsequence, that is has a some gap from x. Okay, so this x n k minus x, so for all k belonging to n, right? So this is, let's say, another property star 2. This is, let's say, star prime. Okay, now what we know that this subsequence has a further subsequence which is convergent, right? So by according to the according to our due to the property of xn, property of sequence xn, we have, or there exists, a further subsequence xnkl, right, such that xnkl converges to x, and this would mean that for epsilon naught, okay, the same epsilon naught, there exists n naught such that this xnkl minus x is less than equal to or less than epsilon naught for all l greater than equal to n naught, right? Now you see here what you are saying. See, xnkl, this xnkl is a subsequence of xnk, right? So these are elements. So suppose my sequence was xn1, xn2, xn3. Okay, this was my this sequence. Okay, xnk. Now from here you are getting another subsequence, right? So this is my xnk and this is xnkl. Okay, now this subsequence are coming from here only, like maybe I am putting it here. So this is my xnk1, the second one would be this, or third one would be this, but these xnkl are nothing but these elements, right? So what I'm trying to say, if I write it in the set form, I can say that this is the property of subsequence, right? So x and kl, where l is from natural number, is a subset of x and k, where k is from natural number. It's just the notation, right? Okay, so this is by the subsequence, like this is what we mean by saying subsequence. So this, obviously these two are contradicting, right? This is saying, this star dash is saying you that x and k is away epsilon not away from x, and this is saying no, some elements are close to x, which is not true, right? So this star prime and star double prime contradicts each other, and so our assumption is wrong. Hence xn converges to x. Okay, so hence we are done. So if you have this property of the sequence that every subsequence has a further subsequence converging to the same limit point, then you can say that the original sequence is also convergent and they are converging to the same limit point. Okay. Okay, if this is done, let's move to the third problem. So what this problem tells, that suppose that the adjacent elements are very close. See, this is telling you that for large n, the sequence is very close. The two adjacent subsequential sequential terms are very close to each other, right? This is what it means, right? That in limit, that is for large n. So if you want to write it in using definition, what you say, that for any epsilon there exists n naught such that this xn plus 1 minus xn minus 0, which is does not make sense, this is less than epsilon for all n greater than equal to n. This is what it means. It means that this term is becoming very close, these two terms. So the adjacent terms are becoming very close for large n, right? Okay. So now the question is, due to this property, can you say that the sequence xn is convergent? What do you think?
Yes, sir, it is convergent.
Okay, but that's not true. I understand that it seems, right, it seems that okay, it should converge because they ultimately they are becoming very close, but that is not true, and I'll give an example for that. But what is true is that uh, there is some another condition. Okay, so I'll mention that. So suppose, okay, this is telling you that they are becoming close, but how, in what sense they are becoming close, we don't know. I mean, what is the rate of becoming close? So suppose you have this kind of property, that xn plus 1 minus xn, they are less than equal to so some c times r raised to the power n. Okay, where r is belonging to 0 1. Okay, so r belongs to 0 1, so r is strictly less than 1. In this case, see there, if you take limit, okay, so let's take limit n going to infinity, xn plus 1 minus xn. Okay, so you know that this is greater than equal to 0, and so this term, as n goes to infinity, this will be going to 0, right, because r is less than 1. So in this case, this limit goes to 0. Okay, so in this case, if you have such property, then you can prove, so you can prove from here, how should I write, so this implies xn is convergent. Okay, so maybe this you can take it as an exercise. Okay, and I'll give you a hint how to prove that. So you just use, so maybe I'll put it here. So maybe first let me explain what is the difference. So here, this condition, in if you have this condition, then the result is not true. But if you know that how they are becoming close, if you have such kind of rate, so this is giving you the rate how they are becoming close and close, right? If you have some upper estimate, in such situation, you can actually give the convergency. You can say that the sequence xn is convergent. But when you have just this point, see, then you cannot. Okay, so this is a general condition. This is telling you that the limit is going to 0, and this is a particular situation where the limit is going to 0. If you have this particular situation, this one, then obviously the result is true. And how you can prove that? So you can basically, here you can prove that this sequence becomes Cauchy. Okay, so maybe I'll just give a hint somewhere. So how to prove it is, you take n greater than equal to m. Okay, strictly greater than m maybe. Then you say what is xn minus xm. So this is xn, you just add and subtract xn minus 1 plus xn minus 1, and then again minus xn minus 2 plus xn minus 2 minus so on. At last you will get plus uh, xm plus 1 minus xm, right? Now you use the triangle inequality, so you'll get xn minus 1, xn minus 1 minus xn minus 2, like this way. And then you will have c, you can take common, you will have rn plus rn minus 1 plus dot dot dot. You'll ultimately from here you'll have rm. Okay, now you show that this you can make it very small. Okay, you can make this, because you know that this is a kind of geometric progression where the this is 1 by r. Okay, so you can make this small. Okay, and in this way you can prove that this xn is a Cauchy sequence, and hence you are done. But over here you cannot use just this definition, okay, just this condition to guarantee that the sequence is convergent. Okay, but in this particular case you can. Okay, so intuitively it seems that it should be true, but it is not. Okay, so can you think of some example? Again, now since I have told you the answer, that the sequence, the result is not true, can you think of some sequence which is divergent? Then we'll try to figure it out, that to for this condition, that whether that condition holds or not. So can you give an example where the sequence is divergent? No? What is the simplest divergent sequence? I just told you a few minutes back. So what about this xn equal to n? This is divergent, right? Yeah. But is this condition holding true? So what is the difference? Xn plus 1 minus xn. What's the difference here? This is always going to be 1, right? So if you write it on real line, okay, so say n equal to 1, then you have 2, then you have 3, then you have 4. So this gap is always constant, right? So you have a proper gapping between two numbers, right? So you have a uniform gap which is 1 over here. But what you can do next is, so suppose now I'm taking another sequence xn which is root n. Okay, now let's take. So this is 1. Let me write it in this fashion. So this is 1. What is root 2? Root 2 is 1.4 or something like that, right? So it is bit here, root 2. What is root 3? Root 3 is 1.7. So let me write it here. So root 2 is 1.4, let's say. Root 3 is 1.7 something. Root 4 is 2. Root 5 is, what is root 5? I don't know the value. But anyway, what I am trying to say here is, let's see, here the gap is 0.4. Here the gap is 0.3. Here the gap is, or I am not writing the more decimal points, but you can see that here the gap would be much less. So suppose here is, if it's 3.5, here it would be 3.2. So what I mean to say, that this gap is not going to be a constant. Okay, so this, when I take just root n, then the gap is decreasing. Okay, and I'll show that, okay, in fact it is going to 0. But this is kind of intuitively what I'm trying to make you understand, that how I'm getting to this example, or how you can think. So since I have answered you that, okay, the answer is going to be that statement is false, now you can think of, okay, if the statement is false, I can start with some divergent sequence and then try to look at if this condition holds true or not. This. Okay, so I started with this example, and then we saw that, okay, this condition is never going to be true because we have a uniform gap. But now when I'm saying that root n, if I take, I hope that I can get such thing. By the value at least it seems, although I'll establish that thing. Okay. Okay, so now let's come to the problem. So my example would be, so the statement is false.
One question. In the first example which you showed, where xn is equal to n,
Yeah, yeah,
we are all that the sequence is divergent.
yeah.
The point is that it does not satisfy the first function or the first condition where you say
Correct.
limit
Yeah,
from n to infinity xn minus xn is xn plus 1 minus xn is not equal to 0.
correct, huh?
So that does not fit into my
No, no, no,
description
no,
at all.
no. Okay, I think you misunderstood what I'm trying to say. So what I'm saying, that to get the counter example, I'll start with some example. Okay, so I, my
Okay.
first choice was okay, I took this x n raised to equal to n. Then I saw that okay, the limit is also going to be 1, so there is a uniform gap. So this is not going to help me. So now
Okay.
my next case is okay, let's
So we're
take
trying to find out a counter example, starting with what we know obviously is not an example for this case.
exactly, yeah. So then
Okay.
I
Okay.
went to another, I mean,
Something
searching
like
for
a
another
root n,
example.
yeah. So where the xn plus 1 minus xn would be decreasing, maybe it goes to 0. That
Yeah,
is another
exactly.
example. Okay.
Yeah.
Okay.
So this is not an
Now
example.
we'll find, sorry, now we'll find an example where actually the sequence has this limit of 0, but the sequence is still divergent.
Yeah, so you know
That
that
is what
this
it
root n
was.
is
Okay.
divergent, right?
Hmm.
Root n, we know that root n is going to
Yeah.
infinity.
Yeah.
Now I'll show that this, the limit of two adjacent term is going to 0. That is the thing what I need to show now.
So isn't boundedness also required? Maybe.
No, no, no. Why boundedness?
No.
No.
Because
If
root
if
n would not be
no, see,
bounded.
if the sequence is bounded, okay, then it cannot be divergent, right? So I am saying that the sequence has to be divergent.
Hmm.
Yeah.
Hmm.
So
Okay.
are you
Okay.
still thinking that this root n will not satisfy this condition? Is it the issue? Do you have a feeling that root n will not satisfy this condition?
No, I'm just thinking that
Mm-hmm.
how to explain this. Uh, it would be unbounded, right? Because root n would be unbounded as a
Yeah.
sequence. So there would, yeah, kind of, there would be no limit for that.
No, no, no. You cannot say that. So in this case, you will
Ah,
see.
ah, okay, yeah, yeah,
See,
got
so
it, got it,
as
got it,
n
got it.
becoming as n is becoming very large, root n
Yeah,
root n plus one will be very close to root n.
it's a root n, yes, yes,
So the
yes.
gap would be decreasing, and this is why I explained it through this example. Okay, so I mean, just
Mm.
trying to motivate you that actually it will
Yeah,
be
yeah,
true.
got the
Yeah.
point.
Okay. So okay. So now my example is that let's take x n to be root n. Okay. Now let us try to compute what is the difference. So this is root n plus 1 minus root n. Now how do you usually try to solve this? So we'll try to rationalize it, right? So it's the best thing. So now I'll multiply it by root n plus 1 plus root n upon root n plus 1 plus root n. Okay. Now this would be n plus 1 minus n, and in denominator we have root n plus 1 plus root n, right? So this is 1 upon root n plus 1 plus root n, right? Now you just take limit. So what you get is, so limit n going to infinity xn plus 1 minus xn, this will be 0, right? So now you got that. Okay, now are you satisfied that this will be, this will hold for this root n? Yeah. So this example satisfies this condition. Okay, but, and so this is the condition what we wanted. Okay, so maybe I and also you can see that this xn is not convergent. So xn diverges to plus infinity. Okay, in fact you can, I can give you some more example. Okay, so do you know that the series 1 by n is divergent? I hope you know. Do you know this? Do you know this thing 1 by n? I don't know, have series started in your lecture session or not? If you have this, then I can give you example, otherwise I can leave it as of now if you don't know.
Yes, sir, I know.
Okay, so then we can leave it, it's not an issue. But the main thing is that using this also you can just construct an example. It's very easy. So how should I say? Okay, leave it if you don't know, or if you assume it I can show you. So suppose I told you that this series is divergent, and so the limit is going to be infinity. Okay, if you sum this up, and what you do, you take partial sum. Okay, so this was n from 1 to infinity. Okay, I will define xn, or let's say k. Okay, so this will be k equal to 1 to n, 1 by k, that is 1 plus 1 by 2 plus 1 by n. Okay, in this case, if you see xn plus 1, so obviously you can see that if you take limit here, so limit n going to infinity xn is going to be this k equal to 1 to infinity 1 by n, sorry 1 by k, and this is going to be infinity, right? This is what this you have. Now the question is, let's see whether the adjacent terms would be very close or not, right? So now when you take this xn plus 1 minus xn, if you subtract this, okay, then what you get is 1 by n plus 1, right? And you know that this is always going to be converging to 0. So this gap, okay, this gap is going to 0, but the sequence xn, which is the partial sum, is converging to infinity. Okay, so under the assumptions, okay, this is what you don't know, but assume this is true, then this is another example. Okay, so this, if you assume, you can see this. So the terms are getting close and close, right? They're not too uh, far, but in limit that sequence is converging to infinity or diverging to infinity. Okay, so this is another example. So maybe, I guess you will see this somewhere, maybe in lectures, or when the series will start. This is a very common thing, right? Okay, so more precisely, if you have this 1 by n raised to power alpha, okay, so this series is converges. Okay, so this series converges if alpha is greater than 1, and diverges if alpha is less than equal to 1. Okay, so this kind of result is true. So you'll see this, I'm sure. Okay, okay, so okay, is this, I hope that this problem is clear to you, and you just try this one. Okay, so in this case, when you have this kind of estimate, then you have that the sequence is convergent. Okay, do you have any doubt, or should I proceed? Okay, if not, then let's proceed to the next problem. Okay, so over here you have kind of lower bound for these two adjacent, difference of two adjacent sequential terms, and then you have to prove that this sequence xn is convergent. Okay, so the hint is, so this I think I mentioned in the last also, that this theorem, that if you have a sequence xn, okay, which is increasing, so monotonically increasing, and you have, what should I say, bounded above, okay, then the sequence, this is the assumption, so This is assumption. Then the conclusion is that the sequence xn is convergent. Okay, so we'll try to use this theorem to establish this. Okay, so this is the hint. Okay, now over here it's clear that this sequence we cannot say whether it's increasing or decreasing, right? We have no idea. So for increasing we need xn plus 1 minus xn should, if it is greater than equal to 0, then we know that this is a increasing sequence. Okay, and then we can go for looking whether it is bounded or not. Okay, anyway this is given to be bounded, so what we need to check that whether it is increasing or not. We cannot conclude from here, right? So we'll try to use some other stuff. So what we'll do, so okay, so this is the hint that we have to use this result. So what we'll do, so the idea would be, let me write it here itself. So construct another subsequence, construct a sequence yn using this xn's. Okay, construct a sequence yn such that yn is increasing and bounded. Okay, so now to show that, so let us look at this inequality. Obviously to guess such sequence we'll have to use this kind of inequality, right? So from here what you can see easily that this xn plus 1 minus xn plus 1 by 2 raised to the power n, this is positive, right? So somehow we want to define a sequence yn so that yn plus 1 minus yn is equal to this, and then we can say yn is increasing, right? So what we'll do, okay, so this is the hint. Okay, and this is exactly the solution. So let me write it further. What we have is that xn plus 1 minus xn plus 1 by 2 raised to the power n is greater than equal to 0 for all n belonging to this natural number, right? This is what we have. So now here I can write, so see here you have to define yn plus 1. So xn plus 1 is there, xn is there, so this is part of yn plus 1, this is part of, so this will be minus, oh, I shouldn't write it in this way, but what I'm trying to say is that this whole thing should be written as yn plus 1 minus yn, right? Now what I'll do, I'll define yn plus 1 to be xn plus 1 and plus something or minus something. Okay, so now I'll try to write this one. So we have xn plus 1 xn, so I'll try to write this in two, I'll divide it in two terms, 1 by 2n. So what one can do is, if you notice here clearly, you can write 1 by 2n as so 2 by 2n minus 1 by 2n, right? This is the obvious thing what we can do. Now this is nothing but 1 by 2 n minus 1 minus 1 by 2 n, correct? So this, okay, so this is what I was trying to tell you. So over here what we can do is this, I can write it as xn plus 1. So see, with highest one we'll have to take the highest order. So with xn plus 1 I'll have to take this term, right? So xn plus 1 minus 1 by 2n minus I'll have xn, and then with this I'll take this one minus 1 by 2 raised to the power n, right? Then this would be my yn plus 1 and this would be yn, correct? So this is how we'll choose this yn. So my definition would be that consider the sequence yn given by yn equals xn minus 1 by 2 raised to the power n minus 1. This will be my yn. Then what we have is, yn plus 1 minus yn. From above we know that this is greater than equal to 0 for all n. That is, this implies yn plus 1 is greater than equal to yn for all n belonging to n. Right? So this proves, or this tells you that yn is increasing. Okay, and okay, so this is increasing further. Moreover, the sequence yn, see this mod yn is nothing but less than equal to mod xn. Okay, let me write it here. Mod yn less than equal to mod xn plus 1 by 2 raised to power n minus 1, and this is less than equal to, so now xn we know is bounded, right? So this mod xn plus 1, this I can bound it by 1. So again, this is some finite thing. We can bound the sequence yn by the bounds of xn. So this tells me that yn is bounded. Okay, so this yn is bounded and monotone. So what we can say is, so the sequence yn is convergent, right, by the theorem what I just mentioned. Increasing, bounded, and we have this. Then this implies that xn, what was xn? Xn is nothing but yn plus 1 by 2n. Yn plus 1 by 2n minus 1, right? Now we know that this sequence converges to 0, and this we said that this is convergent. So this whole sequence is convergent, right? This is just by the algebra of limits, that if xn and yn are convergent, then xn plus yn is also convergent. So using that thing, we have this kind of result. So we ultimately concluded that xn is convergent. Okay, so here basically the hint how you can think is basically, see, you were given that xn is bounded. Okay, so whenever you see that xn is bounded, you already know that there exists a subsequence which is convergent anyway. Okay, but here you have some more information of this kind. So your goal would be to, let's try to prove that it is increasing also, but clearly over here we cannot figure it out, right, that xn is increasing. Still we cannot guarantee that xn is increasing. So you see here, this yn, we have proved that this is increasing, but this thing is decreasing, right? So we cannot say that xn is increasing at all, right? So we should not hope to get monotonicity of xn anyway. In fact, it is not true. It seems from here, right? So we cannot conclude anything about xn. So what our next goal was, okay, xn we know that it is bounded. Let's try to find some other sequence using this xn, so that the resulting sequence is bounded as well as increasing. And for increasing, we have to use this estimate, and this is how, using this estimate, I decomposed into two parts so that I can write I can define the sequence yn, and then we were lucky that, okay, we got this yn to be increasing as well as bounded, right? So using the boundedness of xn and this term, we got, okay, yn is bounded. Now after concluding that yn is convergent, here also we were lucky that this sequence is convergent. If this was not convergent, we could have not concluded. Okay, so using all these things, we got that the sequence xn is convergent. Okay, any doubt from this problem? Okay, Okay, so now let's proceed to the next problem. So from now on, the questions, whatever I think is okay. So this is somewhere which requires a bit of analysis, but more than that, other most of the problems are calculative. Okay, so we'll be a bit quick here, maybe. Okay, so the first problem tells you that you have to find the limit of this problem. Okay, where a is, so what is the limit of this where a is greater than 0? Okay, so I think I already, I mean, somehow solved this problem before. So here xn, you can write it as a raised to power 1 by n. As I mentioned, that when you see this kind of power in a very simpler situation, just take log, right? So define yn. I think I already proved it. Just a second. I think in the very first problem. Yeah. Okay, I proved n raised to the power 1 by n. Okay. Okay, so this part. So this is already proved, right? So this I already proved that this is equal to 1. So see question 1. And this is also similar, like, so as you know that again same logic, so I'll just be quick here. This is much simpler than that, log of a. Okay, so now here xn was this, I took log, so yn is defined as log of xn. So here define, we should write here log of xn, which is this, and you know that this converges to 0 because this is just a constant, doesn't matter. So 1 by n goes to 0, so this goes to 0, and this proves again that yn goes to 0, and this proves xn, which is exponential of yn, converges to 1. Okay, so this is also going to be the limit of this is 1. Similarly, I mean, it's much more easier, but anyway, here we don't have to use the bound for log because it's just a constant, a is constant, so we have this. Okay, so let's proceed to the next problem. Okay, so here the question is that suppose you have been given a sequence xn, okay, and the property is that the subsequences, so this represents the odd subsequential term, so x1, x3, x5, right? So this is x1, x3, x5, and so on, whether this one is the odd even sequences, sequential term x2, x4, x6, and so on, right? So the question is that you know that these two sequences are convergent. So can you conclude that the original sequence is convergent? What do you think?
No,
No,
no.
you know
If
the
they
example.
converge to the
Yeah.
same limit,
Please say, repeat it again.
if they converge to the same limit, then we can say that.
Okay. Yeah. So what you said is actually correct. Okay. So but in general we cannot say that, right? So do you have some example for that when you don't have such general result? The example is very common. I think you must have seen this. So what you said is correct. When both the limit will be same, then the sequence is convergent. But what in general we cannot say that. So we will have to find a sequence which has two subsequences. I mean, the odd sequence and even sequences are converging to different limit point. Then there is a hope that that would be a contradiction, right? So can you give the example?
-1 to the power.
Exactly, yeah, correct. So if we take xn equal to -1 raised to power n, then we have, so the odd sequences are just -1, -1, -1, so on, whereas the even sequences are 1, 1, 1, and so on. So this converges to 1. So x 2n minus 1 converges to -1, x 2n converges to 1, So these two are convergent, but xn is not convergent. Okay, these are the oscillatory sequence, right? So xn is an oscillatory sequence. Okay, so this is false. So this is statement. Okay, so there is nothing about true and false. So we have disproved that this xn is not convergent. Okay, now as she mentioned, okay, which is correct. So maybe I'll write it here. So suppose xn, so suppose, or in addition, let me write the, in addition to our assumption, assume that limit x to n minus 1 is equal to limit x to n. Okay, then the sequence xn is convergent. Okay, so now let us, so this is maybe, okay, let me put the start. So now proof. Okay, so do you know the proof, like how to establish this? You already answered it, but do you know the proof of this? It's actually obvious, like, I mean, obvious in the sense that, see, here the issue was that one of the sequence is converging to another point. So it's like this one, right? So I'll just give a pictorial representation. So it's like x1, x2, x3, x4. What is happening here? See, this x1, x3 and this odd sequence is going to some point here, let's say. Okay, so suppose, I mean, this point here means, suppose you have this real line, so it is going here. So that means these terms are becoming close to this neighborhood, right? Whatever neighborhood you choose, that these are concentrating over here in this region. Whereas this, suppose this limit point of this one is going here. Okay, so these are concentrating on this point. So if you look at the sequence xn itself, then you know that you cannot find that after this n naught, right? So what we have to prove, that this xn minus x has to be less than epsilon for all n greater than equal to n naught. Whatever n naught you choose, the next one of the points, so suppose this is my n naught, whatever n naught, the one point is going here, the next point is going here. So obviously it is not going to be the, it is not going to converge, right? But if both are same, then obviously you can argue that the sequence is convergent. Correct? So it's just a matter of writing. Okay, then otherwise the result is very obvious. Right? Suppose all the things will now go to here, whatever, whether it's odd or even, nothing. So everything is going here, and then you can conclude. So do you want a proof of this, or you can try, or do you want to try it? Yeah, you can tell what to do. Yeah, what do you want? Do you want the proof, or should we proceed to the next part? No reply. Okay, if you want, I can give the proof. So it's just the way of writing. Okay, so I'll just be a bit quick here. So like, I have to prove that this xn, so suppose this limit is x. Okay, so I have to prove that this xn is convergent and the limit is x. Okay, so the claim is, so let me give the proof. so my claim or to show that xn converges to x. Okay, so what I'll do, let epsilon greater than 0 be any real number. So the proof would be same how I explained you through pictures. Okay, so I choose any real number now. Then so what we have, so we know that x 2n minus 1 converges to x. So this means that x 2n, so okay, let me write in words. So this means there exists n in 1 such that this x 2n minus 1 minus x is less than epsilon for all n greater than equal to n1. So this is the first thing. The second thing is x 2n converges to x. This implies there exists n2 such that this x 2n minus x is less than epsilon for all n greater than equal to n2. Okay, so for each of the sequences we got n1 and n2. Now the point is we just need to find a common n, right? Because this x2n minus 1 and this x2n both are nothing but xn, right? So now, okay, so let me write it properly. So xn, if I want to write minus x, so this is going to be either x 2k minus 1, right, or x 2k, right? There are only two possible, either n is even or n is odd. Now we know that this is also less than epsilon and this is also less than epsilon if k is greater than equal to n1, and this is true if k is greater than equal to n2, right? So in this case what we can say, so let me write it here. So k greater than equal to n1 means that 2k, this means that n which is equal to 2k minus 1 is greater than equal to 2n1 minus 1. K greater than equal to n2 means n equal to 2k. Okay, so these are two cases. This is case 1 and this is case 2. So in this case n is greater than equal to 2n1, sorry, n2, right? So what you can take, so take n, so for n greater than equal to maximum of, we choose n1 and n2, right, or 2 times n1 n2, what you have is this xn minus x is always going to be less than epsilon, right? Right, so just because these xn are nothing but this only x, right? So it's very obvious. So you got the answer. Okay, so this proves this result. Okay, now I'll be just using this result. So let's say this is R1 or just R. So this is my result R. Okay, now using this result, so let's go to the second problem. So this first problem was very easy. The second problem says that suppose you have a sequence xn, okay, and what information you have, that x2n minus 1, x2n and x3n. So you have an additional condition that x3n is convergent. So earlier you just had two subsequences, the odd sequences, the even sequences. Now you have one more sequence is x3n. Okay, so now using the convergence of these three subsequences, you have to prove that, okay, so the question is to prove or disprove, but this result is going to be true. Okay, and to establish that result, we'll prove first the result. Okay, so I mean we'll try to show that this is true. So over here, so let me write the idea first. Okay, so let me write here itself. So the B question is given, what you have been given is x2n, x2n minus 1 and x3n are convergent. Okay, so to show xn is convergent. Okay, so my claim is that limit x2n minus 1 is equal to limit x2n. So if I somehow prove that the limit of odd sequence and even sequences are same, then we are done by this result. Right? We have proved here that if the limit are same, then the sequence is convergent. So we'll try to prove that this limit of these two subsequences are same. Okay, then result follows, or conclusion, or result follows, or conclusion maybe. Conclusion follows by R. Right? So now our goal would be to prove this claim that the odd sequence and the even sequences have the same limit. Now how to do that? So somehow we'll have to use this x3n thing, right? That the multiple of 3 that is convergent. So do you find any hint that how to do that? So you just have to play with the subsequences of these things. So the one thing if you notice that 3n has odd and even both sequences. For example, 3 is odd. So if I write x3n, what is it? So x3, x6, x9, x12, x15, x18 and so on, right? So one is, these are odd part of this. So these all are part of x2n minus 1, right? While these ones are part of x2n. That is the basically the hint. So we have taken odd, even, and now we have taken multiples of 3, which is again, which can be, whose sequences again can be thought of as a subsequence of odd and even, right? So this is the hint, like this is how you can actually crack that the limit of these two sequences are same. Okay, so this is the thing over here. Now how the question is how to do that. Okay, so this is the idea, okay, more or less this is the way how can you can prove it. Okay, so now let us go to the actual proof. So maybe I can delete this one. Okay, so what you can do is so suppose how should I write? So suppose this x2n, okay, this is converging to x, or not x2n, let's say x3n. So just as I mentioned, suppose suppose x3n, suppose x3n converges to x. Now because of these two, I know that x6n, okay, which is, how should I say, so we'll say that x, I'm taking another subsequence of this x3n, x6n, this is converging to x. So this I can write maybe like this, x 2 times 3n or 3 times 2, how should I write? So maybe I should write 2 times 3n. Okay, let us see what. So this is also converging to x. Similarly, what you can say is that x 3 2n minus 1. Okay, this is x 6n minus 3. This is also converging to x, correct? So what I have done is basically, so here I should write 3 into 2n, then it would make sense. So what I am doing here is that this n, I am choosing this even and odd. So both, now since x 3n is converging to x, both of these subsequences are converging to x. This is the obvious implication, but the point over here is this. So now what you can actually see, that this subsequence, sorry, this and this is a further subsequence of x2n, right? This one is a subsequence of x2n, and this one is a subsequence of x2n minus 1. So what I can say is, so I will just kind of put a remark on the thing, that this, okay, let me write in the next line maybe. So let me say this is 1, this is 2, further this x2n, okay, sorry, x6n is a subsequence of x2n, right? And this x6n minus 3 is a subsequence of x2n minus 1, right? And the limit of these two are x. So, and limit x6n is equal to limit, or should I write in this way? Just a second. Yeah, so limit and x2n minus, sorry, x6n minus 3 and limit, okay, so this is equal to x, right? So okay, I've just rewritten it, but the point is that, okay, so I should not mention just 3. The important thing is that you see this x2n, I have the assumption that the sequence x2n is converging to x. Sorry, we have that x2n converges. We don't know whether it converges to x or some other point. Okay, so the thing is, how should I write it? Okay, so suppose x2n converges to some y, then the subsequence also has to converge to y, right? But we know that this subsequence is converging to x. Okay, so maybe I should write here. Okay, so in the assumption I should write this. So suppose x3n converges to x, x2n converges to y, and x2n minus 1 converges to z. Okay, so suppose we have this assumption, then, and now it's better to write in this way. So x6n is a subsequence of this, and x6n converges to this, and limit of x6n is equal to limit of x2n, right? This is just the property of subsequence, right? So if a sequence converges to y, then this has to also converge to y, subsequence. It cannot converge to some other point, and this tells you, so maybe I should write in this next page, the subsequence of this. So limit x6n is equal to limit x2n, which proves x is equal to y. Again, same thing. So is a subsequence of, so limit x6n minus 3 is equal to limit x2n minus 1, and this tells you that this is equal to x equal to z, right? I hope this was the assumption, right? So this converges to this, and so we got this, right? So what we have done is, we basically knew that x3n converges to x. From there we derive two subsequences, x6n and x6n minus 3, which are again subsequence of x2n and x2n minus 1. Okay, So this x6n is convergent to is subsequence of x2n. Using the fact we prove that the limit of this x2n is going to be the same as the limit of x3n, right? This is what we proved. In the same way, we prove that the limit of x2n minus 1 is same as the limit of x3n over here, and this proves that this y and z are same as x. So that means ultimately thus limit of x2n minus 1 is equal to limit of x2n, and both are equal to the limit of x3n, which is x. This proves the claim, right? This was my claim, that both the limit has to be same. Is this clear? So what I initially told you, like using the fact that if you notice that the sequences of x3n are nothing but the subsequence of x2n and x2n minus 1, like, right? So that's all I have done. So I have chosen the even multiples of 3 and odd multiples of 3, right? So this is even multiples of 3, this one, and this is odd multiples of 3, which is again a subsequence of the even sequence and odd sequence. Okay, so hence we are done. Okay, so this proves the B part. Now let us come to the, so is this clear? Like, I hope this was clear. So do you have some doubts, or should I proceed? Okay. Okay, so now we'll be calculating some limits, which looks quite complicated, but there is another way of showing this. So you must have seen this result, that limit n going to infinity n raised to the power 1 by n is same as, if both the limit exist, then they are going to be the same, limit n going to infinity an plus 1 by n plus 1 by n, right? This you have seen, this kind of result. Yeah. So we'll be using this result, okay, to establish this, I mean to evaluate, because solving these things looks difficult, but if you formulate it in this way, it would become simpler. We'll see how. Okay, so let's proceed with the A part. Okay, so in this case A, the ANs are given by, or xn, whatever you say, is n factorial upon n raised to the power n and e raised to the power minus n. Okay, so now let us look at the ratio an plus 1 upon an. So what do we have? So n plus 1 factorial, n plus 1 raised to the power n plus 1, and then e minus n plus 1, right? In n we have n factorial, so we have to divide it by n. So I'll write n raised to the power n, e raised to the power minus n, and then we have n factorial. So clearly, like, I can write it as n plus 1 into n factorial. This can be written as n plus 1 raised to the power n, and then n plus 1. This can be written as e minus n into e minus 1. Right, now it would be easier. So you can clearly see this n factorial cancels with this one, this e minus n cancels with this one, this n plus 1 cancels with this one. So what we are left out with, e, and then you have n upon n plus 1 raised to the power n, or in other words, e times 1 upon 1 plus 1 by n raised to the power n, or you can remove 1 here, you can put it here itself, right? So we have just divided by n in numerator or denominator, that this is what we get. Now if you take limit n, you get e, and then you are getting 1 upon limit 1 plus 1 by n raised to the power n. Okay, and this you must have seen at least in calculus, that if you have 1 raised to the power infinity kind of thing, then that converges to, so let me write the general result. I don't know if you have seen it or not, but this is true, right? So limit n going to infinity, if you have 1 plus k upon n raised to the power n, then it converges to e raised to the power k, right? So when you have 1 raised to the power infinity form, you write e upon this, so e raised to the power this times this, so you get e raised to the power k, right? So this is kind of calculus thing. From calculus you have this kind of result. So if you apply it here, what you get is e times 1 by, so this is converging to e, so you will eventually get 1. Okay, so when we see that computing this looks bit weird, but when we write it in this form, n plus 1 upon n, we got a simpler version and which was easier, right? So this is how you can get the answer for the second one as well. So let's look at the second problem. So you have n factorial square n raised to the power 2n. Sorry. Okay, so we have this. Now if we try to write the ratio, so we have n plus 1 factorial square upon n plus 1 2n plus 1, right? And then we have n raised to the power 2n n factorial square. So again we will do the same thing. So here I can write it as n plus 1 square and then n factorial square, right? Here we have n to n, and here what we can do is, so n plus 1 2n, and then you have n plus 1 2, here n factorial square. So this cancels with this cancels with this. So what we have is again the similar kind of thing. So 1 upon 1 plus 1 by n raised to the power 2n, right? So again if you use this kind of thing here also, so you can get here 1 by, okay, so let me write first limit. So here you calculate limit n going to infinity, n plus 1 upon an, this will be e 1 by e into 1 by n times 2n, so which will give, sorry, which will give e square. So the limit is e minus 2. Okay, is this clear? Yeah, okay, so now let us move to the next problem. Okay, so the second one is quite interesting. Okay, so first let's see the first problem. So here again you have to calculate the limit of this. First you can see this n plus sin n square upon n plus cos n. The second one is you have to evaluate the limit of cos n factorial a pi. Okay, but the main difference is that the number a what is given here is rational. Okay, and then you have to find the limit. Okay, so let's begin. So the second one is a bit, I mean, not complicated, you just have to handle it carefully. Okay, otherwise it's simple only. So let's begin with the first one. Okay, a part. So if you look at the limit, it seems that it's n and then you have some bounded term Here also you have n plus some bounded term, so it should be, the limit should be kind of 1, right? Because, so suppose, sorry, yeah, so I'm saying this is n plus sine n square, right? So it is like bounded by, it's a sine n square is like a, you can consider it as a constant kind of thing, that it is not going to play very much role in the convergence because it's a bounded thing what we have. So it's like n upon n, right, this thing. So this gives a hint that okay, we should try to prove that the limit is going to be 1. I mean, from there we can guess. Okay, so this is my claim. So claim is that the limit n plus sine n square upon n plus cos of n, this is going to be 1. Okay, and I'll prove this using epsilon definition. So let epsilon greater than 0. Now let us look at this n plus sine n square upon n plus cos n minus 1. This difference. So this is going to be n plus cos n, then n plus sine n square minus n minus cos of n. So this clearly cancels out. What you have is sine n square minus cos n. Again, as I mentioned, sine and cos are bounded, so let us put it as 2 upon, so 2 upon n plus cos of n. Okay, now here we have to get some bound for cos n, right? This is the place where we have to use, where we'll have to use triangle inequality, but not the usual one. But what we'll use is this one, that mod a minus b. Okay, this or a plus b, this kind of thing you must have seen, that this is mod a minus mod b, right? This inequality. So this is giving us the lower bound, obviously because it's in the denominator, we'll in the lower bound. So we'll be using this inequality. So using this, okay, so let me write it here itself. So using this, I'll get n plus cos of n, this is less than equal to mod n, which is n, minus cos of n mod, right? Now we know that cos is bounded by mod cos is less than equal to 1, so this is greater than equal to n minus 1, right? Okay, so using this, I am getting here 2 upon n minus 1. Now we know this one is goes to 0, right? So this goes to 0, so this proves limit. Okay, I mean, okay, if you want epsilon definition, then I can say that this is less than epsilon if, so 2 upon n minus 1 less than epsilon implies that 2 less than epsilon n plus 1, sorry, n minus 1 epsilon n, and then minus epsilon, so you'll get n greater than equal to 2 plus epsilon upon epsilon, which is 2 by epsilon plus 1. So if n is greater than equal to 1 plus 2 by epsilon, right? Okay, so this is my, not, this is not the n naught, but n naught would be just integer which is greater than, natural number greater than this, just greater than this. Okay, or so this is my, how should I write? So n naught will be just ceiling function, right? So 1 plus 2 by epsilon, so the integer just greater than this. Okay, so this proves that this limit is going to be 1. Okay, okay, now let's come to the b part. So is this clear, like this one? Yeah, okay, so now coming to this one. Okay, So why we are saying that A should be rational or irrational? Why we are making even a point? The reason being that, you see, when you are going to expand this n factorial, so if my A is in the ratio that P by Q form, okay, then there will be a cancellation and the resulting term would be like cos of some integer times pi, right? Some integer, so this is some m times pi, and about which we know. Otherwise it could be very random, like you don't know the value of cos. I mean, when this is not a integer value, some fixed thing has to be done. And this is why we are choosing A to be, I mean, this is why A is given to be Q. If A is not in Q, the result would not be true. Okay, so over here, let's see what will be the terms. So before guessing, let's to guess that what will the limit, let us try to look precisely how the sequence looks. Okay, so maybe B part. So suppose that A is equal to P by Q, okay, where obviously the GCD is going to be 1, and moreover I'll assume that Q is positive. Okay, so P belong to Z, Q belong to N, and GCD of P comma Q is 1. Okay, this is how we can write any rational number. Okay, that's not a problem. So when you write this kind of thing, now we'll have to, so see, the terms are n factorial A, right? And we have to make sure that that is an integer. So n factorial A, if you write, this is n factorial P by Q. And now we to remove this Q, right, as I mentioned, that so that we can guess cos of some m times, I mean integer times pi. Okay, to remove this I'll choose n. So to deal with the convergence, we can choose, we have to look the behavior of the sequence for large n. So now I'll choose, so for n greater than equal to Q. So this is a fixed quantity, right? A is fixed, so P and Q are fixed. So for n greater than equal to P, n factorial times P is going to be Q minus 1 factorial, sorry, times P, right? Because Q will cancel out. So we'll have this. Okay, so this is for n equal to Q. So, okay, let me write. So, how should I write? So let me just expand it then. So n factorial Q would be n minus 1, so on till Q minus 1 times Q. Sorry, Q plus 1, and then you will have Q minus 1 factorial times P on Q, right? So this is how n factorial looks. So when n is greater than equal to Q, that means n is equal to Q plus K, where K can be 0. So when n is equal to Q, this term will not be there, right? Obviously. Okay, so for n get, so this is the general thing how we can write. So now this can be further written as n minus 1 till Q plus 1, and then you have Q minus 1 factorial times P. So clearly this is an integer, right? So no doubt. So for n greater than equal to Q, n factorial time A is given by this, correct, which is an integer. Now, okay, let me tell you this thing. So cos of m pi, what is this? So cos of m pi, if suppose m is 1, so cos pi is, or m is 0, then cos pi is 1. When m is 1, sorry, yeah, so when m is 1, then it is minus 1. So this m, if it is even 2k, then we know that the cos is going to take value 1. Otherwise, when m is odd, it is going to take value minus 1, right? So now, did you get the answer? What do you think from here?
-1.
-1. You are saying the limit would be -1.
-1 to the power some 1 -1 1 -1 like this.
Is it? Look bit more carefully.
1 minus
Okay.
and 0 also.
Uh, okay, let me give you a hint. So far we have said that this is z, right? It's natural number. Sorry, integer. Now can you tell me about this q minus 1 factorial? Okay, so okay, let me write this. So q minus 1, like let me write 1 factorial is what? 1. 2 factorial is 2 times 1, which is 2. Okay, anyway. 3 factorial is 3, 2, 1. 4 factorial is 4, 3, 2, 1, right? So except this case, 2 is in all the terms.
Okay. It's even.
It's even, right? So it's even
Then
for
it is
large q. I mean q greater than equal to 3, let's say. Then q minus 1 would be 1. 2. So what I'm saying is q minus 1 factorial is even for q greater than equal to 3. That means I am putting some condition on q, right? So why I'm saying, so this is done. Now this q, okay, so q is given to you, q is fixed. Okay, so you cannot say that q I will take 3, q I will take 4. You cannot say that. But what you can play with n and not with q, right? So this is just a remark. So this is not going to be very useful, but this is a thing that we should note over here. Let me just resize it. So how now we can deal it? So suppose q is 1. Okay, so let me write first some case by case, then we can combine together. So when q is 1, okay, so if I take, so see, I want this q. So when, okay, so n, if I take n greater than equal to, so how should I say? So see, this q is a fixed thing. N you can choose anything. I mean n you can choose after some point, because I want to deal with the convergence. Okay, so if I choose n greater than equal to 3, let's say, okay, then this n factorials time p by q, okay, q is 1, so this is going to be even, right? Is even, n greater than equal to 2 only, because n factorial will be even. If q is equal to 2, so for n greater than equal to 3, I can say that n factorial p upon q is, no, not n greater than equal to 3, because it will be 3 into 2, right? And then p upon 2, so n greater than equal to 4, right? Now I will have 4 here, so now is even. Okay, sorry. Now when q is greater than equal to 3, we know q minus 1 factorial is even, so n factorials times p by q is even, right? So just a second, so this is even. So see, I just, why did I just erase? So this is q minus 1 factorial is even for q greater than equal to 3, and here we are in the case q greater than equal to 3, so q minus 1 factorial is even, and then this is true. Okay, so in all the 3 cases what we have seen, right? So this one, finally this one, okay. So if I combine all these cases, so what I can write, so n factorial a, which is equal to n factorial p by q, is even for n greater than equal to, so this tells me n greater than equal to q, right over here. Oh sorry, where did I write? Now for n greater than equal to q, right, from here. Okay, in the other two cases, okay, so this is the case, dude, so let me write this star, so phi by star. In these two cases, when q is 1, you are taking n greater than equal to q plus 1. So this I can write q plus 1, right? Here I can write q plus 2 over here, because q is 2, so I can write n greater than equal to q plus 2. So overall what I can write is, for n greater than equal to q plus 2, so whatever q you choose, if it's 1 then also it's satisfied, when it's 2 then also it's satisfied, right? In general we know that for n greater than equal to q this is true. So this is even for n greater than equal to q plus 2, and this tells you that cos n factorial a pi is equal to, so I wrote here, when it's even we are getting the value 1, so this is equal to 1 for n greater than equal to q plus 2. So for large n, the value of cos or the sequence is a constant, right? So it's called eventually constant sequence, right? So this tells me that limit n tending to infinity cos n factorial a pi is equal to 1. Is this clear? Is this okay? So what we did, we just write a as p by q form, the usual how we write rationals, and then we saw that n for n greater than equal to q, we are getting this n factorial p by q is integer. Moreover, if we take n greater than equal to q plus 2, okay, then the integer or n factorial a is becoming even integer, and in that case we know that the cos value is going to be 1. Okay, so that's the idea. Yeah, is this okay? Okay, if it's fine, let's proceed to the next problem.
Hello, sir.
Yes.
Sir, if Q is negative, then what happens, sir?
No, that's why I chose q to be natural number, right? Because rationals is what? See, I mean,
But
if I
in
take p
question,
to be
sir,
integer, that is enough.
but in question asked that Q is also maybe negative also, sir.
Yeah,
That's
yeah,
why I'm
true. So see, you have p by q. Suppose q is negative. So I can write this as p upon minus q, right? Or minus q tilde, where q tilde is minus q. Or let me write it in this way. Minus of minus q. I can write it in this fashion, right?
okay, sir.
And now this minus I can say minus p upon q, minus q. Now this is positive. So each rational number you can write, because the reason being that I'm taking p to be from integer. So generally when you write p by q, you say p q belong to z and q is non-zero. But here I'm saying q belong to natural number. That is also enough. Did you get the point? So
Yes,
here,
sir. Yes.
so here I can write q in natural number because I can throw the negative sign on p. So, okay. Okay, so the next question is like you have to find the value of this thing. So this problem is like you just have to notice the way how this product is behaving, and then you get the answer. Like this is, there is no technique involved in this problem. So So how you can do is, so let's start with smaller version, like let's take n equal to 1, let's take n equal to 2, and then you will see the pattern. Okay, so for if I take n equal to 1, okay, so let me say this is my xn. Okay, so x1, let me write xn. So xn is pi k equals 0 to n 1 plus x raised to the power 2k. Cut. Okay, so my x1 is what? 1 plus x raised to the power 2k, which is, so this product k equal to 0 to 1 1 plus x 2 raised to the power, is it 2k or 2 raised to the power k? Sorry. Okay, 2 raised to the power k, so which is nothing but 1 plus, so x raised to the power 2 raised to the power k would be x square, and the other one would be x plus x, sorry, this is x and this is x square, right? So this is how x1 is. Now x2 is 1 plus x 1 plus x square, and the other would be 1 plus x raised to power 2 square, so it is 4. In the same way x3 would be 1 plus x 1 plus x square 1 plus x4 1 plus x8, right, and so on. So let us notice this one. If I further multiply, what I get is, so first multiply by 1. Okay, no, first multiply with 1 from this side, so I'll get 1 plus x. Now multiply by x square, so I'll get plus x square plus x cube. Correct? Over here the same thing, so this is, I'll just write what we have obtained above. So this is 1 plus x square plus x cube. See, the power where it ends, it is starting from there, this power. So 1 plus x raised to the power 4. Again we'll do the same thing, first multiply by 1 and then by x4. So when I multiply by 1, I am getting the same thing, so it is 1 plus x square, sorry, x3. Next I am multiplying by x4, so I am getting x4. So see, here the x cube ends and now x4 starts. So x4, x5, x6 and x7, 3 plus 4, right? Again, if you do the multiplication, you'll start from 1 plus x plus so on, and you will end at x8, and till here you have x7, right, this one, so you'll end at x15, and the next one x4 would be what? 1 plus x 1 plus x square 1 plus x4 1 plus x8, and then the other would be 1 plus x raised to power 2 raised to power 4, right? So 2, so here you will get x raised to power 16, right? So here where it ends, the next power is this one. So when you do here, you will get 1 plus x dot dot dot, here x15 and here x16, so you'll get x31, right? And the next term, if you go x5, you'll get 1 plus x32, x raised to power. So in this way what you can write is, so this xn can be written as 1 plus x square plus dot 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 plus, at last what we do, so over here what we did x raised, so here it was x 2 power 4 and this was x 2 power 4 minus 1. So here we'll do the same thing. Here last term is x raised to the power 2n, right? If you see here, put k equal to n, x raised to power 2n, and the previous one where it ended, what is x raised to power 2n minus 1, and then we multiply it, right? So ultimately this term become x 2 raised to the power, what it would be, so it would be x 2, so it's 2n plus 2n minus 1, right? So it is 2n plus 1 minus 1. It is x 2n plus 1 minus 1, right? So this is nothing but 1 plus x square plus dot 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 plus this. Right, and this is something that we expect, because in the xn plus 1, this is where this will be multiplied by x2 n plus 1, right? If I calculate xn plus 1, then this plus 1 will be multiplied by in this term, right? Okay, so this is what we get. And now this is what, this is just a geometric progression, right? Where the first term is 1 and the r, or the what the common multiplier factor is x. So this I can write it as a upon 1 minus r, which is x, upon 1 minus x raised to the power n. Right? This is the formula what we have. Sorry, I'm writing the wrong. So 1 upon a upon 1 minus x raised to the power n. Okay, so here the, see what is the, how many terms are there? So it's not, this is number of terms are 2 raised to the power n plus 1, right? So these many terms are there. So this is my n actually. So this I can write it as a upon 1 minus x raised to the power 2 n plus 1 upon 1 minus x. And this is possible if mod x is less than 1, right? Right. So now you just, I mean, this is the answer, but you can further simplify it. What will be the simplification? Okay, that's it. So this is the answer. This is my term. Okay. Okay, but you have to find the limit value, right? So this is the xn. So now limit n going to infinity xn, if I do, so this 1 upon 1 minus x will come outside, and then you have to take limit n going to infinity 1 minus x raised to the power 2 n plus 1, right? And now you see this factor, as n goes to infinity, so this goes to infinity, and this x is less than 1, so this goes to 0, correct? So this whole limit is equal to 1. So the answer is 1 upon 1 minus x. Okay, so this would be the answer that you just, so this product is equal to 1 upon 1 minus x. So this product converges to 1 minus x as n goes to infinity. And this can be seen also, right? The way we were writing it, you see, if you know the expansion, if you expand this, so I mean this is, or you can say that this is another proof of getting the expansion of this 1 upon 1 minus x. So this says that this series, where is it? Yeah, so this series is converging to 1 upon 1 minus x. Okay. Okay, so do you have any questions? Okay, then let's see you. I'll see you next week then.